Good morning, everyone. Welcome to our presentation today on optical switching for AI scaling, data center automation. Honored to have several guests who are going to talk about OCS. This is the topic that's generated a tremendous amount of interest among our clients and among the industry, much more than we had originally anticipated when we first published a paper, or Scott published a paper probably about a year and a half ago. So I'm very excited today to have four knowledgeable speakers on this topic from different parts of the industry. I'd like to introduce Peter Rueda. He's the general manager of the switching business unit at Lumentum. Hi, Peter.
Thanks, Andrew. Glad to be here.
We also have Bob Shine. He's the VP of Marketing and Product Line Management at Telecent.
Thanks, Andrew. Looking forward to talking to everyone today.
Also, Daniel Perez Lopez. He's the co-founder and CTO of Ipronix.
Thank you, Andrew. It's a real pleasure to be here.
And then finally, we have Steffen Koehler. He's the Senior Vice President of Datacom Product Line Management at Coherent.
Morning, Andrew. Thanks for having me on.
All right. And finally, last but certainly not least, is Scott Wilkinson. He's the lead analyst here at Cignal AI for optical components. Scott,
yeah, you can.
Thanks for kicking this off.
And, you can say least. That's fine. Among these people, I'm happy to be least. But thanks very much.
So my name's Andrew Schmidt. I'm the directing analyst here at Cignal AI. You're all in listen-only mode. We encourage you to ask questions at any time using the Zoom interface. So just go ahead and fire away. Free, doesn't cost anything. We will conduct the Q&A at the very end, but it's always helpful, particularly for me, if you put your questions in early so I can begin writing them down and getting ready for the Q&A portion of the webinar. So Steffen, why don't you go ahead and take it away?
Thank you, Andrew. Pleasure to be here. As Scott mentioned earlier, all optical switches, as they were originally called, they haven't been new, or they're not new. They've been around for 25 years. And switching speed wasn't a critical parameter in the applications that Scott mentioned, telco networks, and then primarily lab automation, right? So that's what limited deployments, because the use case wasn't there. But what's changed now with AI and hyperscale networks in general, but AI specifically, are requirements for software automation. Not just an operator saying, hey, I want you to switch port A36 to B15, but actually continuous software control of switches. And so to really prove it in volume, we had to replace that OEO packet switch. That was the restriping that Scott talked about. But that means reliability that has to be similar to at least an electrical packet switch that it's replacing, or better. Because in the early days of data centers, a 1% failure rate of links was okay. They were just simply overbuilt with Ethernet redundancy. That started changing a decade ago, and that would be a complete disaster today in an AI network, a 1% failure rate. So we've had that application that Google publicized. There's an emerging application in the backend scale-up network. That application isn't here yet, but it's emerging and people are talking about it. I'll talk more about it. Also, workload balancing, where you're now switching from workload to workload, or even job to job within the workload. So these and others that Peter referenced earlier are the constantly emerging applications that will not only bring OCS into the network, but it will drive down the cost of OCS as we get to higher and higher volumes. And those lower costs will spark even newer applications. So this is a slight tweak on the original application. This is the spine switch layer. Everybody talks about replacing all the spine switches, but you don't necessarily have to replace all of them. You can replace most of them. And again, Google publicized their cost and power savings. Lower latency, because now you're going through here at wire speed if you're going through the OCS, as opposed to buffering and reading packet headers. You can also reach to multiple places. This doesn't have to be uniform. It doesn't always have to go to the leaf. It can reach to the TOR. It can reach to an element inside the rack. That's something that hasn't really been talked about too much recently. But this is a sort of more generalized version of that original application. In scale-up clusters, obviously what's used today in many cases is NVLink to connect interconnect GPUs. And I think we heard from an earlier speaker about originally a node was one GPU, then it was 4 GPUs, now 72 in one rack, and now we're going to multiple racks, and that can largely be done with an OCS complementing, not necessarily replacing, but complementing an NVLink switch or something equivalent. I want to talk a little bit more about this concept of interconnecting AI clusters, because that can mean several different things. It's not just one hodgepodge interconnect, but we can now create essentially a meta cluster. If we have a cluster that was built here, another cluster that was built here, we can make them look and feel like a single larger cluster. We can also schedule maintenance using an OCS. As you migrate workloads off of this cluster, maybe this takes 5 minutes. Every time a new workload comes up, you just move it to another cluster. Eventually, you've completely offloaded this cluster and you can do maintenance on the cluster. We can go to other buildings in a campus, of course. So all these things are new ways to dynamically reimagine and reconfigure how these clusters are working together. Let me talk a little bit about the digital liquid crystal technology that Coherent has selected. As you've heard, there are multiple technologies being considered. Many folks are doing MEMS. We heard that piezo, robotic, and silicon photonics. At Coherent, we've chosen a digital liquid crystal. This is not LCOS. It's not liquid crystal on silicon, but it is a digital liquid crystal. And think this is something that's been deployed for years in displays all over the world. So what we have, obviously, because it's an OCS, is an all-optical switching fabric. Port counts from 64 by 64 going up to 512 and eventually going higher than that. One of the reasons that we thought this was a good technology to use was the very low drive voltages. The fact that there are no mechanical moving parts here. The only thing that moves is the orientation of a liquid crystal matrix. And this gives us some very nice properties that I'll talk to a little bit more. One of the ones I'll really talk a lot about is the fact that this is a proven technology. Besides the display world, this has been used in WSS, in wavelength selective switching, at our company for a couple of decades. The way it basically works is we take a single pixel, which we send light through this pixel, and by changing the properties of the digital liquid crystal, we can either orient that light to go up or down or to go left or right. So now we have a two-dimensional steering element in a single pixel here. And if we put a bunch of these pixels into a panel and then make a sandwich, make a stack of these panels, then we have an OCS. So light comes in on a fiber, we collimate the fiber, put it into free space. We put it into this fabric here. So now what we're doing is changing the direction the light is going. We orient it up, down, left, right. Simply bounce it off a folding mirror, do the reverse coming back, go through another sandwich of these liquid crystal panels, and then back into fiber. If we put this all together, we end up with a complete OCS in a chassis. So I mentioned we've been doing this for a while. We've been doing it for a couple of decades. We've got in WSS using this technology. Over 160,000 have been deployed worldwide, right? That's over 30 billion device hours. And just as Peter mentioned in his remarks, if we look at what fails, it's not the optical element. If we look at actual field data over those 160,000 units deployed, and many of them are deployed in undersea networks where, reliability is super, super important. It's almost never the liquid crystal. It's the good old drive electronics. In the rare cases where something fails, almost never the optics. So why is this? Again, it's the things I mentioned earlier, the lack of moving parts, the fact that it's a digital liquid crystal. We either turn the matrix this way or we turn it this way. There's no in-between state, and it's very low voltage. So one of the key parameters is crosstalk. And this is more and more important now in these newer applications. I think most of you have probably heard about all the discussions about link flaps. Link flaps are what kill AI training models. And if you have crosstalk in somewhere in your network, that leads to bit error rate getting worse. That leads to long FEC tails. And if they get long enough, your link flaps. And if your link flaps and you're in the middle of a training sequence, you've got to go back to the last checkpoint. That could be 2 hours ago. So we'll do anything in the world that we can to avoid link flaps. So crosstalk can be both static crosstalk and dynamic crosstalk. Static crosstalk is simply when nothing's changing, but you've got aggressor ports shining light into the output that should be really reserved for the signal you're trying to measure. But then even worse is dynamic crosstalk. So this happens when one port is switching, and how much does that switching activity impact another port? And some approaches, unless they have a shutter mechanism, if they've got this input port here talking to this output port, and you want to move it to the lower one, you essentially sweep it. It's like sweeping a searchlight all the way across all the other ports. And that's dynamic crosstalk that these other ports see. Digital liquid crystal, because it's based on the polarization state of a liquid crystal, if I start with this port and now I want to switch to the bottom port, I fade out on this port and I fade in on this port, and I never cross the other ports. So that is one of the inherent advantages that we feel that liquid crystal brings to the table. Speaking of tables, here's our little table of why we chose it. Coherent is a MEMS company. We have lots of MEMS products. We are a silicon photonics. We do silicon photonics. So we didn't have much of a technology bias when we decided what to do here. So we looked at switching time. And again, no one's talking about doing packet level switching here. We're doing workload level switching here. So in our case, we specify about 100 milliseconds. So that's workload to workload. Insertion loss, I'll echo what Peter said in his remarks, 3 dB at the end of life is what we're looking for. Of course, a patch panel is going to simply have the insertion loss of one connector pair. But still you have relatively low insertion losses. And I'll talk about some mitigation for even that amount of switching, that amount of insertion loss. Drive voltage is very low. Instead of a couple hundred volts, we're talking single digits. And drive voltage speaks inherently to failure rate of the electronics. I mentioned the electronics would dominate. We already talked about crosstalk, right? So very low crosstalk in this technology, no moving parts, and very simple to control because it's all digital control of these pixels. So that's why we liked liquid crystal for this application. Everybody talks about the optics, but we are talking about building a network appliance here. So the things that are important in any reputable and reliable network appliance piece are important here in an OCS, right? It's not an isolated piece of optics. So we use field replaceable units wherever possible. That means we have redundant fans, redundant controllers, redundant power supplies, etc. Right? So you can replace these things in service without impacting the traffic that's going through. But never forget the software. Again, it's a network appliance. So we have to customize the APIs to whoever's using it. I saw already in the chat, somebody asked about standardization. In the Sonic, there is a Sonic working group being formed, a subgroup in Sonic that is looking at OCS and how we apply Sonic as the operating system for an OCS. Sonic was originally written for layer 2 and layer 3, but now we want to bring it down to the physical level. So that's already, the standardization is just starting to happen. One of the advantages we have at Coherent is we're not just an OCS company. We're obviously a very large optics company, and we are a very large transceiver company. And looking at the inevitable insertion loss that you have, of course, you can apply gain that introduces noise and has a whole bunch of other trade-offs. But there are some things we can do to address Scott's 2x plus y problem, where he mentioned the distance we're going is 2x. So x being the insertion loss of the link, and then y being the insertion loss of the optical circuit switch. The FR4 standard, the 400G base FR4 standard, was written with 4 dB of link loss, and it assumes that because you're inside a large data center, you're going 2 kilometers. If you add an OCS, again, if we assume that your end of life insertion loss spec is 3 dB, that means you need to budget now for 7 dB. Now that's X plus Y. But what happens if you're actually making that round trip? The good news is you don't have to double this 4 because there is a standard for 6 kilometer link already defined. Of course, we only need 4. This is going a little extra. So the LR4-6 spec is defined as 5 dB plus now 3 dB. We have, of course, our standard FR4 transceivers and 2x-FR4. Coherent has now released a variant of those transceivers that has the extra insertion loss in the link budget without going to a fundamentally new technology. So we have a 400G FR4 dB transceiver, 400G FR4 transceiver with 3 dB extra link budget. We have a 2x-FR4 with 3 dB extra link budget, and we have a 2x400G LR4-6 where we've got 3 dB link budget. But very importantly here, because everything needs to be interoperable, these transceivers, if there's no OCS present, they do not violate the basic standard of 400G FR4 or LR4-6. So they're still fully interoperable with a standards-based transceiver. Yet if you have these on both ends, you've got an extra 3 dB of link budget. So we're not violating the overload spec on the receive side or anything like that. So these are the kind of things that Coherent is pioneering. We fully expect other transceiver manufacturers to follow suit. And now what we're doing is creating a whole ecosystem where the OCS and the optics in the data center are all engineered to work together, but not in an engineered link. It's still in a standards-based link. So in summary, unlike 25 years ago when we all talked about all optical switching, we now have new technologies that make these, that are really tailored to the hyperscale and AI and machine learning applications, right? Reliability is paramount, and we think that liquid crystal is really a standard bearer there. Low in crosstalk, and again, the ecosystem of transceivers. And as you've heard from, I think, every speaker so far today, new applications are constantly emerging. There was one application, 2 years ago. Now we're looking at more and more applications. You've heard that from all of us. So we currently have a small switch. By small, we mean 64 by 64. We have a 320 by 320. We are we'll next release 512 by 512 and get up to 640 by 640. I don't think that is the ultimate limit, but let's say that's in the medium term where we at Coherent are headed. We think there's a good feature set, a good set of specs here. And we think this is the highest reliability outside, of course, of a physical patch panel robotic type application. So with that, I will conclude. Thank you very much.
I'm here, just manipulating on my end. So we have a ton of questions, sorting through them here. If we've received a lot of questions on specs and the performance of one person's switch, probably not going to address those. Well, we're definitely not going to address those during the Q&A. So if you did ask, you asked anonymously, go ahead and re-ask with your name, or just contact me and I can put you in touch with the appropriate people. Otherwise, all of the presenters get a copy of the non-anonymous questions, and I'm sure they'll follow up with you. The first question that I wanted to get to was there's some confusion on cost per port versus switch. I mean, Scott, I think you might have had a slip there. What you want to talk about the cost of these systems in terms of how you're modeling them?
Yeah, you ever read something on a slide in the middle of a presentation and realize, oh, that's not right. 25K is not per port for Google. The modeling for Google was about 25K per system. The original cost per port was closer to $500 per port. We're below that now. We have a goal of getting way below that, but certainly not 25K per port. That would be terrific for all the manufacturers here, but not so great for the people who had to deploy them. So I'll fix that in the slides before we upload this.
Okay, so along the lines of cost, we had a question, wasn't voted top, but I thought it was pretty interesting, so I'm going to fire away, and maybe each of the panelists can address. But to what degree do you see cost being a barrier to adoption? If the price of your product were to be cut in half, do you think that the amount of volume would suddenly surge, or are there other barriers that are preventing wide-scale adoption today? And maybe we can go ahead and start off with Bob. Why don't we start with you, since you've probably deployed more than anyone?
Right. So I think there's cost of the system, but then also we talked about it with the cost of the software and implementation. When you talk to the Google people, they talk about their software team was probably larger than their optics team. And so if you reduce the cost of the system, it doesn't remove that software cost and implementation cost. So I think it's really finding the right use case that is easier to implement first, and then you'll find it going forward. So I don't think cost is a barrier today.
Okay. Steffen, Peter, Daniel?
Yeah, I'll
Any
jump
comment
in.
on cost?
Yeah, I mean, cost always matters, but I have been a little bit surprised at how much it's the focus is on power in these applications, power efficiency and the benefits of power, and it's clear the pressure on the data center operators on power, so that is eclipsing cost. But to be sure, cost does matter, and I think there's elasticity of demand to cost, especially as you get into these some of these applications are cost sensitive, but I think power is the power savings versus the Ethernet switch, and then also latency and the latency, because that gets better utilization of your GPUs, and then just the reliability impact again is worth a lot. So I would say cost is not the premium one, but it always matters.
Yeah, I would like to add my 2 cents here. I think cost gets more important as soon as you are getting closer to the GPUs in this case. So for some applications, especially if you are thinking about the scale up, whether it is a direct substitution of what is today or a layer 2 of what is today, I trust me, the cost becomes one of the top 2 most important metrics.
Okay.
Yeah, but to answer your question, what is today's barrier? I think Bob nailed it. Right now, people need to know how to control these things, and doing the optics, we've proposed 4 different ways to do it, right? So it can be done. It can be done with good enough specs to do it, but it needs to be controlled. And until you know how to control it and you've worked out that entire control plane, that I think is what's limiting the timing. And as that goes away, as more and more people do what Google spent all those years doing, I think you'll see the adoption swiftly take off. But that's in the short term the barrier. right? Years down the road, sure. How much does this cost versus a packet switch? But first, you've got to be able to control it, and it's got to be reliable so that you're not going back into your network constantly.
Okay. So it sounds like particularly for scale up applications, it's not just the software, it's also the cost becomes more important because the volumes probably go up. So along the lines of deployment, there's been a lot of messaging from Google on their use cases for OCSs, their internal development, the software. I know that there's a lot of activity going on outside of Google, but there hasn't been a lot of public disclosure of where people are in terms of their deployment plans, things like that. Scott's taken his best guess at what deployment looks like by modeling incremental applications at hyperscalers. What do you guys think in terms of the ramp and the deployment? Aside from some of the technical barriers like software and maybe cost, how do you see an average large customer rolling out this technology, and how do they knock down the problems to do it?
I think the early adopters will be the larger players as opposed to kind of the smaller, often smaller users are early adopters, but here, we saw Google as the kind of standard bearer early adopters. But because they're going to be larger players, I think we'll see large pilot deployments. I mean, one of the things that characterizes AI deployments is the lumpiness. For any of us who sell transceivers or other things into AI networks, we're constantly noticing how orders are never smooth. They're very lumpy. They're very big, and they go on. I think we'll see that with OCS. I think we'll see a lumpy pot. No one's going to put 10 units out there. It's going to be, okay, we start with 300 units, right, before we go to 3,000. So once we get out of the lab, you'll see these pilot cases. I think that's how we'll see deployment over the next couple of years start in these chunks.
Yeah, I concur. I concur with that. It is, it's these big 4, 5, 6 big hyperscalers who are going to be driving this. They've got the scale to make the investment in the control plane, unlike this, like the smaller players and the more diverse applications. And I think Scott's forecasts actually look pretty good when I look at that, and it seems like that's pretty representative of what we're seeing, how we're seeing the market take shape.
Okay. Let's see. We had a number of questions about latency and also compatibility with different bands. What bands do you see as being the primary application? I mean, O band, but how do you see the importance of transparency for different bands? Is this something that's crucial, or is most of the volume going to be concentrated in the O band?
I'll jump in. I mean, clearly it's O-band. Initially, it's O-band, right? All these interfaces are O-band, and that's critical. I think a transparency in two dimensions. Yes, there's interest in C-band. Nobody wants to shut out the C-band because part of the value proposition here is that this is evergreen. They can move forward. Also, transparency in terms of higher line rates, which as I pointed out. I think there's a to a degree, nobody wants to introduce something that's going to prevent them to go to higher line rates, even if it is within the O band. So I think transparency on both of those fronts is important, but clearly it's O band in the initial intra data center applications. That's where all the
if
focus
somebody
is.
wants C-band, you can sell them a WSS. So that's you have a solution there. I think there's some high level questions about packet switching from a number of people in the audience. And exactly what is the use case for OCS? And as the switching speeds potentially can increase, to what degree are they doing packet switching versus circuit switching? Do you see applications for packet level switching in the next couple of years? Daniel, maybe it's a good one.
I can take that. So basically, depending on the speed of your switch, you can enable a greater granularity for some applications. For example, if you are thinking about machine learning or AI, if you are able to switch faster, you are going to be able to introduce the switching operation within the typical commands and control that are being used in the AI in the AI basically pipeline. So the faster that you switch, if you are able to do this rather than in hundreds of milliseconds, in less than 1 millisecond, or in microseconds, the more granularity that you can introduce. But the reality as well is that for the 95% of applications today, there are some time limitations somewhere else in the network or in the application that actually someone would say, okay, it doesn't make sense to be faster because the bottlenecks are going to be somewhere else. But given said that, we see the interest. In principle, if you are able to do this in sub-milliseconds, let's say 100 microseconds, like our technology, this opens the path for burst switching, which is an interlayer between packet switching and circuit switching. And we are seeing some traction on that area. I honestly don't think that going to the lower layer, which is the nanosecond switching and trying to be faster than electronic packet switching on this regard, makes sense. You will need to solve a whole paradigm to actually enable this, and this will make the integration on current data center even more difficult.
Okay. Anything else that other people would like to add? Packet switching?
One of the things to
Any
consider
applications?
in terms of switching speeds as well, we didn't mention is that right now everything's a PAM4. I mean, Daniel talked about burst switching. That's a different transceiver. Right now, the PAM4 optics on both sides, they take a while to sync up. And if you switch faster than that, you're not getting any benefit. So in order to go to what Daniel's talking about, that's new transceivers. And there's some technologies out there, people are trying to do that, but that's not something that integrates easily.
Good point. Yeah, we need fast sync PAM4. All right, so we're getting past 12:30. I want to end with one question for all of the participants. I think it's a good way to wrap up. Can you talk a little bit about what spec you're getting the most pressure to improve when you look at your particular solution? What is the one area where you see being critical that you need to improve or find a way to help your customer more in that area? Steffen, you want to go first?
Well, given that it's early days, I think everybody's watching reliability. That is table stakes. And so until we have 10,000 OCSs deployed, we're going to constantly be proving our claim of good reliability. So that pressure won't go off until we have a track record. And I don't think anyone's got an OCS track record on that yet.
Okay. I mean, there is a pretty big track record for LCOS and MEMS and WSSs, but
sure, the technologies have it, right? Yeah, but now we've got to prove that the actual box has it.
Okay. Peter, what do you think?
Yeah, I'd agree. Reliability is top of mind for everyone. It's I mean, that's why Coherent and ourselves, we have some advantage, right? Because of our field reliability track record. And then IL, everyone's focused on IL because of the strain it's putting on standards-based transceivers, and that's top of mind. People are having a relook at their link budgets, as I was talking about. I would say IL and everything after that, power consumption and all that, secondary to reliability and IL.
Yeah, insertion loss. So that also, I imagine that impacts the radix size too. As you get bigger and bigger, it probably starts to hit. So talking about IL, Daniel, so what that's not as much of an issue with your solution. What are you guys facing?
So I think that as I mentioned before, the number of applications in the market for OCS is quite diverse. So the number of KPIs we are tracking are diverse as well. I would say that in our case, we have been able to move forward from signal integrity, that was the key question mark around silicon photonics, and we overcome that one already. So the next one in our conversations is cost.
Cost. All right. And Bob, you've been shipping. What where
So
are
the average question we get is, can we go faster? But clearly we're not competing in speed with these other technologies, and so that's a kind of misuse of the application. So really, where we get the more pressure is actually port count. Even though we have the highest port count, that's our best fit, and people want. It's amazing that hyperscalers just want more and more fiber management. And if you think about the scale of the fibers going in, you read it, machine learning clusters have 5 to 10 times the amount of fiber that the CPU clusters used to have. And so the fiber management is just out of control. And so any way we can help people improve that fiber management without taking up a lot of space. Because for these hyperscale data centers, any space not used for compute is not generating revenue. And so they want as much fiber capacity in as small a space as possible. So that's what we're getting pushed.
Okay. Scott, anything you'd like to add in terms of specs? Any thoughts after hearing all the answers?
No, there's no way I'm going to disagree with those guys.
Okay. So I promised to sign off, but we have one question here about its CPO. So I have to ask the question about CPO. And to what degree does CPO have any impact on these switches? Do you really care about what's at the endpoint? Is there anything that you're considering in terms of design or your customers are considering in terms of deployment, particularly imagine for scale up for CPO? Does it matter?
I would
Sure,
like
it
to add,
matters. Sorry, go ahead, Daniel.
yeah, sorry, I will be brief. I would like to answer that I don't think that there is a single CPO thing in the market or hitting the market. So there is a CPO that is kind of DR with a single fiber per transmission. There is a CPO which is bidirectional with two wavelengths transmitting. So the diversity of CPO is there. I think that most of the OCS solutions are relatively flat for the complete O-band. So yes, there are some things that you need to take into account, but not many. I know, Steffen, if you want to add.
Steffen, you were gonna say something?
Yeah, I think Daniel's point about diversity of CPOs is good, but a CPO it's just a transceiver. It's just not a standardized transceiver, right? So because they're non-standardized, we're going to have CPOs initially deployed probably without OCS in mind. We'll have some CPOs deployed with OCS in mind. And until both of these worlds kind of get really standardized, you're going to see people who are deploying both CPO and OCS needing to marry those together from an original architecture standpoint. But a CPO is just a transceiver. And so the OCS fundamentally doesn't care.
Yeah, I'd agree. I mean, CPO is sort of emerging in the scale up and OCS in a different part of the network, but eventually we should pursue the best of both, right? OCS capable CPO transceivers, and then you get the power savings there and the OCS, and I think that's when these converge. I think that's a very powerful future system, right? And they will, but right now they're kind of emerging independently from one another largely.
Okay.
What I would add to that is that CPO, at least right now, when it's just a transceiver, not a large impact. But if CPO starts to replace copper, more optics means more applications for OCS. So long term, it's a good thing.
Mm-hmm.
Yeah. That is what we all hope for, is that we replace the copper. So that it's a great application. I'm going to go ahead and wrap up. We have tons of questions. I think just understanding all the questions on people's minds in terms of specs is really helpful from a marketing perspective.